All right, welcome back. We are Game 2005 and the Fall 2020 semester at George Brown, and it's week 9, part 1 of our broadcast. Might be the only part this week. We're talking about conservation of energy, which is kind of the concept we're going to be talking about today. But first, let's take a look at where we're sitting. We're just after the mid-semester break. You've done your midterm tests, most of you, and you've handed in assignment 1 and assignment 2, which I'm still going through, to be honest with you. I think most of the things that I've seen for both assignment 1 and 2 are good in the groups that you've created. There's some stuff that's not so great, but for the most part, I'm pretty happy with the things I've seen so far. So you can expect pretty good marks coming down the pipe for assignment 1 and 2. Today I'm going to be presenting assignment 3. Let's talk about assignment 3 right now. It's been posted since Monday, and you should have already talked about it potentially in your on your lab on Tuesday. But let's talk about this right now. So this assignment 3, I think, is a very straightforward assignment. It's 2D collision detection and response. Again, this is due week 12. That's Friday, November the 27th, 2020, 2020 at midnight. Let me see if Friday, November the 27th computes. It does compute. It just should say 2020, not 2019. Yay. Let's continue. This assignment is broken down into a couple of parts. Each part should be hosted in a separate scene. So you have an SDL framework that you've been given, SDL engine. You can use that or another SDL framework of your choice. I highly recommend SDL engine as it gives you all the things that you need. The best way to complete the assignment is to complete as much work as possible on your own, and then get together with your partner or partners to get the rest done, so that everyone knows what they're doing. Because in the final assignment for your final test, it's going to be practical. It's not going to be true, false, multiple choice. It's going to help you with your final test. All right. So you're also going to have to acquire or create both your image and sound assets. It's up to you how you're going to do that. I don't expect you to create anything, but if you're going to do it, you need to acquire your assets on your own. And what I'm going to ask is, please do not use the assets from your lab, right? Unless otherwise instructed to do so, or any of the assets that I've shown you in class. Okay, so these assets are your own. Also, I've seen some pretty bad assets as well for assignment 1 and 2, like as in the bare minimum or assets that are inappropriate. That's where you guys are going to lose marks. So please try and keep it so that it is as appropriate as possible for the application that you're making. Excuse me. All right, so let's talk about the base of the project. So all projects will have this base. You will use C++ and the SDL framework provided. So this is SDL engine up on GitHub that I've given you to create 2 scenes. Okay, so 2 scenes this time. The first scene that you're going to make is 2 scenes in addition to the starter scene is what I'm looking at. All right, so 2 scenes. This is really 3 scenes. So 2 scenes and the starter scene. The starter scene is going to basically have labels, a dashboard, if you will. Maybe we should put 3 scenes in there. It's going to be basically a dashboard that will allow you to go from the start scene to scene 1 or scene 2. So that's really what the start scene is going to be. It's going to have your team members' names and student IDs and all that kind of stuff here. And a couple of buttons or other controls which allow the user to go to either scene 1 or scene 2. All right. Scene 1 will contain the physics simulation for part 1, and scene 2 will have the physics simulation for part 2. All right. So there's 2 different scenes here. Both are going to require background images and or a tile map. So please don't leave the scenes black or white. If you do, you'll lose marks. Okay. So a good strategy to do here, because there are 2 separate scenes, is that each member can do their own scene. So for example, if there's 2 people on the group, then one member can do scene 1 and the other one can do scene 2, right? Or you both do scene 1 and scene 2 and take the best of scene 1 from one member and scene 2 from the other member, whichever you guys decide, and then put it together to make a final project. I will not accept multiple submissions for this one. So that means that I want scene 1 and scene 2 to be part of the same project. Okay, so it's not going to be 2 separate projects I'm going to be accepting here. All right. You're going to be choosing the appropriate scale for each scene. So that means like pixels per meter. And you're going to add appropriate variables and data structures to accomplish this. we're going to let the user activate each scene with a button or other control. So it's not going to immediately be on when you enter the scene, all right? You're going to also use appropriate label objects to show key statistics, which may include mass, position, velocity, acceleration, all these kind of things, just like normal, like in assignment 1 and 2. You may again use IMGUI for this, as it has been included in your template, so you can use what's been provided. Allow the user to change the variables for each scene. In this example, update the display accordingly. Okay, we're going to talk about how to do that, and provide the user with a button or other control within each scene to go back to the start scene so that they can try the other scene out. All right, and this is for testing purposes, of course. Okay. Here's your first scene, your part 1, a simple 2D collision detection. Pretty simple, all right? You guys can do this. You should be able to do this with your eyes closed, but here's the details. There should be at least 10 bullets on the screen at one time. You're gonna make a scene where it's raining bullets, all right? In fact, you will only ever have 10 bullets in the game at once. All bullets will be reused. In other words, you're gonna create something called a bullet pool. And I know that Spencer kind of talked about making object pooling before in his lecture, and I think this is a really great thing. It's an optimization pattern, all right? The bullets will initially move down the screen at a rate of gravity, whatever the rate of gravity you decide is. And again, you would be able to modify this with your controls in IMGUI, so you can increase gravity, decrease gravity, and so on. The bullets will appear at the top of the screen at random locations, so it's going to be random places and the bullets are going to come down the screen. Bullets will reset off screen when they pass the bottom border of the screen. Okay, the player will control a sprite that has an appealing texture, spaceship or plane or whatever. You may use a mouse motion or keyboard input to control the player. Okay, if the player's ship gets hit by any bullet, an explosion sound clip will play, and ensure that the sound clip only plays once. This is the exercise. So if you're hit by a bullet, it's not going to play all the way through the ship. Right, it's only going to hit your ship once. Very simple, and this is you practicing how to do simple collision detection with a ship and a bullet. Now, be aware that the player, the person who's using your scene, can turn up the speed, do different things, increase gravity. The things, it's raining bullets. The bullets aren't being fired at the player. They're going to be coming down at the player at the rate of gravity, which means they're going to be accelerating. Please keep that in mind when you're making this first scene. Okay. Questions around scene 1, the simple 2D collision detection scene. If you do, put up your hand and we can take a question now. If you don't, I'll continue. All right, Tam, come up with your question. Come on the mic, please.
For one, about Spencer's lab, he kind of just had a lab where we talk about the advantages and disadvantages of an object pool. I'm wondering, why didn't he just teach us how to do one this week instead of doing it next week?
I'm not sure. That's something that you should approach him with. But I'm surprised that, he's going to talk about it again. Is that what you're saying?
Yeah, but it wasn't even a lab. For mine, it was like the recording was 10 minutes, and then my lab was just a PDF or something that said, read this article and then list out some advantages and disadvantages. I just don't even think that was a class, really.
Okay, I'm not sure about that, to be honest with you. I do apologize about that.
You just went through like what an object pool was and how to do one this week rather than waiting until next week.
Okay, I know he posted a video, and that's the video you're talking about, like that 10-minute video?
Yeah.
Okay. So, again, and he didn't go over the framework at all? Like how to add it into the framework or anything like that?
No, it wasn't really... I didn't find it helpful, honestly.
Okay. Well, I think you should let him know, because he is very sensitive to try and make it as helpful as possible for you guys, right? So please connect with him, because he's in charge of the labs. I want to help you as well. The only thing I can tell you is it's something that you need to connect with. Worst case scenario, what I can do is I can set up an additional session for you guys at some other point where I'll go through things with you. But really, at the end of the day, it's Spencer to do it, right? So kind of work with him if you can, and if you don't get a response, Tam, then connect with me, okay? And I'll see what I can do.
Okay. And then the rest is about the actual part 1 of the simulation.
Talk to me.
I wrote it down here.
Okay.
What exactly do you want to be able to be adjusted? Do you want, like, also, before I say that, do you want the bullets to spawn at different times or at the same time?
Oh no, it's going to have to be different times because I think it's a good idea to have them spawn at different points in the screen at different times. Thank you for that. That's one thing I didn't put in here as a requirement. So, for example, maybe if I was going to make the bullets, I'm just going to draw this out here for you guys, right? Let's do it. So if I was going to design my screen, and again, this is being recorded for us, so we can do this. Let's suppose I have a bullet that is going to be here, right? And then maybe another bullet that's going to be down here. Another bullet might be over here. So randomly off screen, not just on the x-axis, but even on the y-axis might be a good idea, right? And then they're going to fall down, these 10 bullets, at the rate of gravity. That's what's going to happen. So when they hit you, the player object, which will be somewhere down here, again, there's only going to collide with you once, but it'll give randomness enough so that way the bullets will be coming down at a different rate of speed, or sorry, different times at the same rate of speed.
Okay, so I just use a timer for that. I linked the YouTube video in the chat to show you what I've done so far.
Okay, thank you for that.
I basically made it so you can adjust how long between the bullets dropping.
Yeah, awesome.
And then the gravity of the bullets, the mass of the bullets.
Awesome. Maybe what we can do, Tam, is you and I can kind of hook off later on and on Discord, and you can show me this, and we can have more of a conversation around it.
Okay. And then let me see what else I have here. Okay, so then I'll talk to you about what the variables you want to adjust and what labels you want me to show on the screen.
I think things like, the number of bullets. I said up to 10, but you should be able to adjust the number. If I say 20 bullets, then you should be able to create a pool with 20 bullets, as an example. So you should have that. Maybe there's going to be some kind of slider control, as an example, where you can say, here's the number of bullets, right? So, you can have your bullet number here. That might be something you want to think about. I'm just brainstorming here with you, right? So you might want to put that in there. Definitely the rate of gravity is something that you want to put in. The size of the collider, the type of collider that you want to think about using might be a good thing as well to test. Because think about this, you're really testing out your game, right? To figure out if the collider is right. Maybe the bullet texture itself, maybe something you want to swap. So maybe some bullets are shaped like stars, other bullets are shaped like circles, the third bullet's shaped like diamonds. I don't know, right? And then what kind of collider are you going to have for those different shapes? Is the visual collision going to match with the logical collision? Those kind of things is what you want to do, right? So try and give as much variation here as possible. And this is for you to learn how to deal with this stuff. The exercise is very simple, but you can really ramp it up in terms of learning, which is really what I'm hoping for.
Okay. And Herman in the chat brings up a good point. Do the bullets disappear when it hits the player?
I would say so.
Or does it do you delete them, put them back at the top?
Yeah, you wouldn't delete them. Remember the way the bullet pool...
You'd reposition them.
Yeah, so the way the bullet pool would work, right? If bullet pool, if you're going to use it, you have a bunch of bullets that you have in some kind of structure, right? My recommendation is you have some kind of vector, or you could even use something called a deck in C++, right? And what you want to do is, let's say, for example, this is the bullet pool. If you used a queue type structure, so if I was going to do it with a queue, right? And let's just talk about that. Then a queue has a property of first in, first out, or first come, first serve, right? So what happens is, what you want to do, this is a data structure we're talking about, right? Then what you would do is you would load up the the pool from the bottom, right? And it would come out of the top, right? So this is the first bullet that would come out, this one here. When it comes out of the pool, right, you serve it up to be used, right? So it becomes active. You set it as active, right? Let me just put active. And I don't know why I'm getting caps here. There we go. So you make the bullet active, and this active bullet appears in the scene. So it's something that appears, let's say, at the top somewhere or whatever. When it hits your ship, it becomes inactive, right? This could be invisible, or you want to remove it from the scene itself. Okay, so you can do that with remove child as an example. So it goes from active to inactive. Inactive objects go back into the pool, right? So then you always have a fixed pool size. If you decided to have 10 bullets, then there's only ever going to be maximum of 10 bullets inside the pool. You never instantiate or destroy anything, ever. What you do is you reuse every single time. You recycle the bullets that are in here. The advantages of this pattern is you have stable memory management, and what it does is it reduces fragmentation, memory fragmentation. Because what happens is, if I was to instantiate bullets every single time, it actually takes cycles from the CPU. And we don't want that to happen. We want to have all the memory preloaded up front, which gives us a more stable, consistent gameplay and experience. Okay, and you do that for all assets. You preload everything. All right, and this is what the bullet pool would look like. So you do things like on queue the bullet onto the queue, and then you dequeue the bullet off of the queue. All right, and you can use, there is no queue in C++ necessarily, but there's something called a deck class. And take a look at that. You should take a look at that for a structure. You can also use a vector collection as well. One of them. But one thing you want to do is capture that you're going to take a bullet out of the pool, which means the queue could be a collection of bullet pointers. That's what you're going to do, a collection of bullet pointers that you're going to return, right? So what you're doing when you return it out of the pool, it's not available to be used again. So what's going to happen is it's going to go to the next bullet. So it's going to start off at the top, right? It's going to remove this thing, and then the next bullet that's going to be called when it rains down is going to be this one. So this is going to be the next bullet. This one, right? And then when this one's out, it'll be the next one, and the next one, and the next one. It'll keep going down the queue. That's how the bullet pool works.
Okay. The way I have it set up right now, because I know you want pools, but what I did is just make an array of 10 bullets.
Arrays are bad. Arrays are bad. Don't use arrays. Because arrays, yeah. The reason why is because at the end of the day, they become harder to manage. You want to manage collection. All right, that's probably the better way to do it. So something like a collection of bullets, like as in a vector of bullet pointers, or it could be a deck or something else. A list, a linked list, something like that is probably a better structure for you than an array. Right? I'm not saying arrays can't be used for pools. I'm just saying they're not a great. It's not a great structure, and the reason for this is because of, if we're going to try and optimize memory, a vector, as an example, gives us a contiguous memory cells. They kind of create memory right next to each other, right? For pointers, so right next to each other. It's almost like memory management. Also, a vector of pointers, right? A lot of times, what we do is we put them on the heap, not on the stack. I mean, you could have an array of pointers also put on the heap, not on the stack. And really, a vector is just a managed array, but there's a lot of work that can be done for you ahead of time. There's a lot of things that the vector can do that you'd have to program and write extra code for yourself with an array. So that's why I don't think it's a great structure. Hopefully that answers your question.
Okay. And then last thing was, is there maybe a time frame on when the assignments are going to get marked? Simply because it's hard to gauge how well we're doing without any marking structure. Like I could be using the same things I did in assignment 1 as 2 as 3, and then because I did something wrong in 1, it can reflect on 2.
Absolutely, you're right. So if you want to, again, I'm working through them. If you have concerns, please connect with me offline on Discord, and I can go through them with you. Okay? If you have real concerns, like if you didn't meet the or if you feel you didn't meet the requirements or you made mistakes, connect with me on Discord, and then I'll go through your stuff. Okay?
Okay. It's not that I feel I didn't meet the requirements. It's that like the requirements were met, but I don't know if it's done the right way. That's all.
Okay. Fair enough. Yeah. All right. Any other questions around? Again, we're talking about the simple 2D collision scene, the first part 1. All right, let's move on to part 2. So part 2 is really simple 2D collision detection and response. So now this is a little bit more challenging than part 1. Part 1 is really, I'm colliding. Part 2 is, I've got momentum, right? And what we're doing is we have a bouncing ball or some kind of thing that's bouncing, and a player-controlled brick. I'm going to call it a brick. It's not brick breaker necessarily or Pong. What you're going to be doing is you're going to use the appropriate collision detection and response techniques to solve this problem. The bouncing ball will collide with the scene's boundary and maintain most of its momentum. So it needs to have velocity and mass in order for you to have momentum. We're going to talk about that today a little bit. However, some of its energy will be lost and it will continue to slow down. Select an appropriate mass for the bouncing ball and allow the user to change the shape of the ball to a square, triangle, or other polygon and rerun the simulation. So this is part of the controls that you'd be using. The player can move the brick on the screen using mouse controls. When the brick collides with the bouncing ball will shift direction and potentially gain momentum depending on the velocity with which it is hit by the player's brick. Okay, so that right there is a lot, right? Because what's happening is I can transfer energy, right, from the player's brick, from my movement, to the bouncing ball, which means the player's brick also must have some kind of mass. All right, so keep that in mind when you make this. It's not as simple as making Brick Breaker or some kind of a Pong game. It's not like that at all. Okay, so keep in mind what I'm looking for here. All right, questions around this one. Tam, you did a good question of asking. Did a good job of asking questions before. Do you have questions around this one? Since you're you're kind of the spokesperson so far for today.
Okay. Well, my thought process here is, I guess we're going to use a cross product for determining which direction it's going to bounce to.
Remember, cross products is really only for 3D to give us the most value out of it. You might want to use there's an angle towards function that I've given you in your utility classes. So cross product may not be the thing that you want. Okay. Because you're going to use dot product along with, I've kind of created an angle towards, or an angle between two vectors that you can use that's already made for you. So there's some of the math is already there in the utilities. Okay.
What else? I didn't really look through this one yet.
Okay.
I wanted to do one scene at a time.
Yeah, no problem. Yeah, do what you have to do.
I'm guessing it's sort of like a Pong, but the player's at the bottom and it's sliding back and forth.
I didn't really say that, and what I mean by that is it could be anywhere, right? So you can think about it as the brick can be positioned. Some people ask, well, how do you want the brick positioned? Do you want it like horizontal? Do you want it vertical? How do you want it? Because I didn't really say it. So the reality is you could make it so that the controls allow your brick to be in a different orientation altogether. And let me talk about this in a bit. So let's just make a new scene here. So now we have scene 2, right? And here's scene 2, and there's a couple of orientations. You can make your brick this way. You can also make your brick this way. I didn't say which way to make your brick, right? And you should give the player the option to do either, to position the brick this way or this way. It can make it more interesting. The ball can appear on the scene. Remember, you're going to have a start button or something, but the ball can appear on the scene like literally like this, or you can make it come into the scene. It's up to you. Maybe start moving, let's say from here, and you want to make it move in a specific trajectory so that it kind of moves to here, it bounces, and then from here it goes down to there, and so on, and keeps doing that until you can hit it with the brick, right? So you should be able to move the brick anywhere you want. Again, you could limit yourself by creating controls with IMGUI, let's say at the top, that allows you to orient the player's avatar in any direction. So maybe you have some kind of slider or button control, let's say, that gives you horizontal or vertical or some other kind of control for this thing. You might have, again, you want to vary the mass of the ball and the amount of energy that's being reflected. Okay. So hopefully that gives you some ideas of how it works. Again,
well, you say that the ball keeps most of its momentum. Are we like tracking time between it hits the wall, or is it like a velocity based on the angle that it's going to go to?
Angle definitely will do it, because the way it would work, and we're going to learn about this, is if I have a kind of an angle of attack, if I have enough velocity, the ball is going to try and leave the scene, right? So what's going to happen is part of the energy is going to reflect out inside the same angle, the opposite angle of incidence, right? So whatever the angle is here, the opposite angle is going to come out this way. That's pretty simple. So notice that when I go this way, I'm going up in terms of y, right? So my y is going to be negative, right? And then, but my x is still going in the same direction. So x is going to be unaffected, right? So what's going to happen is it's going to go Y, but then what's going to happen is when it hits the wall, then X will become positive, and it'll just reflect back down this way, where Y becomes positive, where X maintains what it was. That's the default. That's perfect collision and perfect response, right? With no energy loss. The energy loss is going to happen because it's going to make noise. Imagine a real world scenario. It's going to make noise. And think about how it can lose energy when it hits this wall, right? What happens? It's not a perfect transfer of energy from the wall back to the ball, right? If it was perfectly elastic collision, then it would transfer all the energy back into the ball, and no momentum would be lost, right? But that's not what we're saying here. We're saying that some energy is being lost. You can come up with a number. It could be something like how much restitution the wall has. Like, for example, how much it absorbs the energy, right? And you might have some kind of meter or slider that kind of you can put here to say, well, it doesn't absorb too much, or it absorbs a lot. It's very, I don't know what you want to call it. It's an absorbing wall that can absorb some of the energy. I don't know, a thick wall made of material or something like that, right? So that's where you can vary the effect of how the simulation runs, as well as changing the mass of the ball and so on, right?
So you have like a mu of absorption.
Something like that, yeah. Some kind of coefficient of absorption, if you will, right? You can also do things like I didn't talk about gravity at all. This is kind of like a top-down game that you'd be using, but if you wanted to incorporate gravity as well, that might be something that you might want to do. For example, maybe as it approaches the top, the ball will have a tendency to drop down if gravity is kind of down here. That's up to you if you want to incorporate gravity, right? So maybe at the beginning there's no gravity, right? And then what you can do is you can add in a little bit of gravity. So it kind of goes up and then it swings back down again, right? And then it bounces a little bit and it stops moving at some point. But if I hit it or scoop it with my brick, then it starts to move again. So it's up to you how you want to do the simulation. I think it's a great practice for you guys to do this kind of stuff, because once you are able to do collision response, there's two responses. The one response is here at the wall, right? So this is the one response, and the other response is when you hit the brick. So if this thing hits the brick and comes off of it, there's the other response right there. Okay. A further one is if we had two balls, right? So and I haven't done this with you guys. That wasn't the plan. But if I had two balls here, and if there was two dynamic objects that hit each other, how would you deal with the response then? All right. Again, I don't expect you guys to do this, but if you had more than one ball, that might be something else you want to include in your simulation. Okay, so that is really your assignment 3. Okay, again, there's three scenes. There's the starter scene, which is your menu scene, your dashboard. There's scene number 1, which is basically getting you to do simple collision detection, and scene number 2, which does collision detection and response. And that's what you've got this in here. Finally, there's a video demonstration. Again, this allows you to talk about your code, your algorithms, and how your game functions. And then, of course, I'm looking for version control as normal. The whole thing is out of 100 marks as before. Okay. Any other questions around the assignment before we move on? All right, guys, let's move on to the next part. All right, so today we're going to be talking about conservation of energy, and let's do a little bit of an energy review. So we know that there are two types of energies we've talked about so far: kinetic energy and potential energy. There's also something else called internal energy. Okay, so think about kinetic energy as the energy of motion, potential energy as the energy of position. We talked about that before as well. And internal energy is things like temperature or those kind of things that we really don't care about too much. Okay, at least not in terms of in game terms. Okay. So there's different types of systems when we talk about conservation of energy. There's non-isolated systems. Again, we're gonna delineate here a little bit, and isolated systems. Non-isolated systems are energy can cross the system boundary in a variety of ways. For example, I can transfer energy from the ball to the wall across the system boundary. Isolated systems where energy does not cross the boundary of the system at all. All right, where the total energy of the system is constant. Okay. And that's also possible for a system. And then Conservation of energy, it can be used if no non-conservative forces act within the isolated system, right? And it also applies to biological organisms, technological systems, engineering situations, and all kinds of things. Law of conservation of energy, all right? And really, there's a few ways to transfer energy into or out of a system, all right? Again, this is adding on to, energy of a system, which we talked about last time, which is work. Work transfers energy by applying a force and causing a displacement of the point of application of the force. Okay, so that's one way. Some kind of mechanical wave, right? In real life, you'd have some kind of mechanical wave, a disturbance that propagates through a medium. For example, things like water. You can move an object because of, energy transferring through the medium, water, or air, sound, as an example. Typically, that's what we when we say mechanical wave, those are the two systems that we're very familiar with: water and air. Air, which is sound, and water, which is some kind of ripple, right? Heat is another way of transferring energy from, from outside of the system into the system. A matter transfer, in other words, I'm adding to the system, right? An electrical transmission and electromagnetic radiation. Again, these last parts right here are probably not really pertinent to game development, but we want to mention them in terms of, hey, they're this part of physics. And there's some examples here of some energy transfer, all right? So example, energy transfer to the handle of a spoon by heat, right? So the spoon itself is the system. Heat is inside of the cup. The heat transfers from the liquid in the cup to the spoon. Energy transfer. Is it perfect transfer? No. Some energy is lost in the ambient air around the cup, right? Energy leaves the radio from the speaker by mechanical waves. Mechanical waves being air waves, right? So what happens is that's how sound works. Sound actually moves the air, and so that it comes to our ear. If there wasn't any air, there's no sound. So again, some of those space movies we see explosions in and stuff like that, really cool. But there's no sound in space because there's no air. There's nothing for the sound to no medium, the medium is so frail or micro, right, that it won't propagate the sound enough. We won't hear the sound, right? We might feel the vibrations if something hit us, the vibration of an explosion, for example. There might be other things, but for us to really hear the sound in space, not likely. Energy is transferred to the block by work. I've pushed the block, therefore I'm transferring the energy because I'm displacing the block, right? Matter transfer. I'm filling a gas tank, kind of thing. Electrical transmission. The energy transfers to the into the hairdryer from the wall, right? And electromagnetic radiation. Energy leaves the light bulb. Electromagnetic waves, in terms of light, leaves the light bulb, right? So these are kind of an example of energy transfer we should know about. Let's talk about the conservation of energy. I kind of mentioned it in the last lecture, where I kind of said that energy is conserved, and when we think about the conservation of energy, it's energy can neither be created nor destroyed, just transferred. Or this idea, the law of conservation of energy. And then the other one is, if the total amount of energy in a system changes, it can only be due to the fact that energy has crossed the boundary somehow. All right, so from somewhere to somewhere. And you might think, wait a minute. That means energy in our entire universe, right, is always the same. And the answer is yes. The current way we think, the physics philosophy that we use today, is that all energy is already in the system of our universe. This is the big system with a capital S. That's it. That is our universe with a capital U, right? And whenever we move things or whatever, we're using energy somehow. How do we get energy? Well, human beings, we eat, right? Eat generates energy. We also have energy loss when we eat. We have in terms of heat and other things. We don't have a perfect transfer or conversion of matter to energy. When we eat something, there's actually there's stuff that we don't use. So there's actually waste products that come out of us eating, and we're trying to convert. We're big energy converters. That's what we are, right? Animals and humans, we're energy converters. We convert matter into energy. Then we use the energy. Once the energy is used, right, we transfer it. Actually, is what's happening. We either transfer it in terms of work, or we transfer it in terms of heat. We also use energy to power our organs. and all that kind of stuff, right? So if you think about it, the energy that we're getting is neither created nor destroyed. All we're doing is we're transferring energy all the time. And if you think about that, everything is a transfer of energy, then it changes your perspective on things. Again, outside of little philosophy. There's also some math involved. So again, the change of energy of a system is equal to the sum of all energy transfer. All right? So whatever the total sum of all energy transfer is the total change in the energy of a system. Okay? And we can look at some of this. This is the actual big formula if you're interested in the math, right? So we say that the change in kinetic energy plus the change in potential energy, that's U, right, plus the change of the internal energy, right, so things like heat, is equal to the total work plus Q, right, when we think about the the energy of a system. And then we have other things here like transfer of mechanical waves, transfer of matter transfer, transfer of energy, electrical transmission, of electromagnetic transmission, and these two things balance. Okay, that's how it works. Okay, and that's what, so established symbols is total work, that's what Q is work plus total heat, right? So the transfer of heat, transfer of work plus transfer of heat, and that's Q. All right, so again, do we really need to know this? No, but it's a good example of when we always, these are the things we really care about a lot in our game. Change in kinetic energy and the change in potential energy and how that equates on the other side, right? When we talk about an isolated system, again, what we say is the change in the mechanical energy of a system is always zero, okay, for an isolated system. Again, notice what I said, the change, delta, right, of energy. What type of energy? Mechanical energy, this is how we read it. The change of mechanical energy of a system is always zero, which means that, and our mechanical energy is the total kinetic energy plus the total potential energy. And remember, we have this swing of energy, right? We move from potential energy into kinetic energy, right? That's what ends up happening. And then we have some kind of energy transfer across the system boundary if we can, okay? Otherwise, it gets reflected inside the system, okay? So this idea of conservation of energy. Now, sometimes we have non-conservative forces that are used as an example, and this is transferred into internal energy or heat. That's what internal energy means for us. All right. So when we have an isolated system, it looks like this. Kinetic energy final plus potential energy final is equal to kinetic energy initial plus, potential energy initial. All that happens is the energy stays the same, right? It's an isolated system. And this is different than what we saw before in a non-isolated system where we can transfer energy across the system boundary with work. Right? And that's the other thing that's missing here. If we were going to do this, we would say the kinetic energy final in a non-isolated system plus the potential energy final is equal to the kinetic energy initial plus the potential energy initial plus work. And this is how we figured out that we can use the law of conservation of energy. We're transferring energy into the system. And they have the same kind of structure that we've used before: conceptualize, categorize, analyze, and finalize is something that they use to describe how this works. All right. So again, we want to form a mental picture of how we want to define the system itself. I think that's the most important thing. Whenever we try and categorize a system, what is the system? As an example that we're looking at, and where is the boundary of the system? Is it, as an example, isolated or is it non-isolated? It's rare that we have an isolated system. Rare, right? That it doesn't get affected by anything outside of the across the system boundary, as an example. Most of the time, our systems are non-isolated. Why? Because we can transfer energy into and out of most systems that we deal with in games, I'm talking about, okay? Again, in the real world, there's many other types of systems, and so it would be different. Okay, so that's kind of what we do. Here is an example of a ball in free fall by using this law of conservation of energy. Again, think about this in terms of, I want to determine a few things about the ball. If I start off, if I have some information, as an example, and I say that, okay, I want to know what the kinetic energy final and potential energy final is at this point, this y as an example in for the ball. We know that as we move the ball higher, that potential energy is related to the total height, if you will, of the ball relative to the game world. Okay, that's what it is, right? So the higher the ball is, the more potential energy it has. Here, there would be less potential energy. If we let the ball go in free fall, potential energy would have been transferred into kinetic energy at this point of height. And what you can do is you can use, again, yi, which is the initial height, and then you have something called the initial potential energy due to gravity. So that's what ug means. The gravitational potential energy, which we're going to talk about later on, which is also equal to mgh, right? And then what we have is our kinetic energy initial is 0, right? Because it's not moving initially. Then when it comes to this point, kinetic energy final is half mv squared, right? And that is your final velocity, whatever that is, velocity final, right? We might know what this is, the y final, from the y initial to the y final. This is the y final. So we have this information. Then we can figure out, well, what is the gravitational potential energy final? Remember, it's made from the height differential between where the ball is in the air relative to the game world's ground, right? Or in our case, the real world. Okay? And we know at the bottom that the y, or the height, is 0, and the potential energy at the bottom due to gravity, gravitational potential energy, is 0 as well. So all the energy is transferred into kinetic energy at this point. Okay. Hopefully you guys are getting this stuff again. Some of this is review, okay? But again, the idea here is that you understand energy transfer, because this is going to set us up nicely, guys, for next week's lecture, which is all around momentum and collision response. We're going to start talking about collision detection and response in 2D, and a lot of this has to do with energy transfer, okay? Not just example of making colliders, how colliders work. That's just one part of the solution. The other part is understanding energy transfer and making it realistic. All right, so again, if we're going to analyze this, we can see that they do the same thing. They just rearrange the equation where we say the velocity final. If I wanted to find the final velocity, then I've just rearranged the equation when it went in terms of kinetic energy and potential energy. And I get something like this. So velocity final is the square root of, and you might want to use this equation sometimes, 2g times h, so the initial height, which is way up there, minus the final height. Okay, and that's how you can find the final velocity, which is kind of a really interesting and simple formula. All right, how about this one? You have a spring-loaded rifle, and this could be like a BB gun, which is what we're talking about here. So you have the initial spring position down here, and then you have the final spring position right here, right? And then what's going to happen is when it goes from the initial position to the final position, so its compressed state to its decompressed state, you're going to have energy transfer from the spring system to the ball, right? Or the ball bearing, or whatever it is that you're transferring. So again, let's conceptualize this. The projectile starts from rest. And again, if you're holding the rifle straight up, which is not a great idea, right? That means, or a cannon, whatever you do, it's going to go up and then come right back down at your head, right? So that's why we don't fire rifles or any kind of projectile system straight up, because it's going to come straight back down, okay? So again, it speeds up as the spring pushes on it. It accelerates, all right, until it gets to the point where it's going to leave the spring, right? And once it accelerates, it's going to fight gravity until it gets to the top of the system, the top of the place where our velocity is 0. Okay, and once the velocity is 0, then it's going to start to fall back down again. When the velocity is 0, it's going to have the maximum gravitational potential energy at the top, right? And we're going to have the minimum kinetic energy, because it's going to stop. The ball bearing is going to stop at the top, and then it's going to start going back down to the bottom. And it's going to transfer between gravitational potential energy into kinetic energy again, just like the previous example. Okay? So again, we know the projectile starts at rest, so the kinetic energy is 0 at the beginning. we're going to choose 0 for gravitational potential energy where projectile leaves the spring, okay? Because we don't know, there's no potential. Think about this as at the bottom. It's sitting at rest at the bottom of the quote-unquote ground, the ground level of the spring. The elastic potential energy here will also be 0. After the gun is fired, right, the projectile rises to a maximum height where the kinetic energy is 0 and the potential energy is maxed, okay? And that's kind of the way we would think about this system. And here's the energy transfer. So again, notice that at the beginning, I'm just going to zoom in here, right? At the beginning, what you have is your kinetic energy is 0. Your elastic potential energy is also 0 for the spring. Your gravitational potential energy is 0. But as soon as we trigger everything, what's going to happen is the kinetic energy is going to be 0, but the elastic potential energy is going to be unleashed, right? It's going to be released, right? And then what's going to happen is the elastic potential energy is going to transfer into gravitational potential energy as the object moves higher and higher, right? When it comes to the highest speed, it's going to have the most kinetic energy as it reaches its maximum speed. And then finally, when it gets to the total height, the kinetic energy is going to continue to deplete until it reaches the total height where it has the most gravitational potential energy. Notice the energy of a system here is the exact same. The system is not losing energy, it's just transferring energy. Okay, so this is the interesting part about what we're doing. I'm not going to talk too much about this, but there's also something called kinetic friction. And it's interesting, the way they talk about kinetic friction in the book that I used is really like two surfaces have what they call teeth, all right? Because we can't see the teeth in objects, right? If I have a book that slides across the surface, really what's happening is the molecules of the book are colliding with or interacting with the molecules of the desk, right? And so there's this teeth interaction that's causing the surface to have friction. And it's almost impossible for us to determine how much friction there is by using the system, okay? Even if we look at displacement, we look at the total displacement that we're moving the object between teeth. So we're saying here's where we start, and then this is the book surface, and this is the surface of the table, and we're moving the book across this way at a certain distance, and we're going to try and calculate the kinetic friction, right? It's hard to do, and that's what it says here in our inside of this logic here. I'm going to move on. So what if we wanted to find the block on a rough surface? How do we figure this out? We start off, again, where we think about what friction is. Friction is as a result of mass. The more massive an object is, the more friction it's going to have, because you're going to use the coefficient of static friction and the coefficient of kinetic friction in order for you to figure out how much friction force is going to push against the block as it's moving. Okay, this is something that we've seen before, all right? It's the same thing when it comes to a block spring system. When I want to transfer energy, when I'm doing work on a spring, again, this is all review in many ways. I'm doing work on a spring to compress the spring. As I compress the spring, I'm doing work, right? Because I'm moving an object, I'm moving the spring itself, I'm compressing it. I'm actually transferring energy into the spring system across the system boundary, and I'm increasing the elastic potential energy of the spring in order for it to, kind of exert force on the block back the other way. Okay, so again, these are all concepts, and you can see how we can work out the kinetic energy final is equal to kinetic energy initial minus the friction coefficient times our distance, right, which is the force that we're using, plus the work of static friction that's gonna stop us. The work of the spring, sorry, it's the spring work, if you will, right? And we know that the final kinetic energy is equal to 1/2 mv squared final, and so we can use this formula to sub into the other one. All right. You can also add adding changes to potential energy. For example, if I have Mechanical energy, so again, mechanical energy in the form of energy transfer from sound or from water, some kind of mechanical wave that comes that transfers across the system boundary, then the change in mechanical energy is equal to the change in kinetic energy plus the change in potential energy, which is equal to a negative coefficient of kinetic friction times the distance. Okay? That's how they figure this out. Again, I'm going to move forward. This is concept stuff, which is largely what this presentation is about. Trying to get you to understand the energy transfer concept, which is really what we're talking about this entire presentation, until we get to this next part. So I'm just going to skip through here. Here's something that we've seen before. In your assignment number 2, you had this idea of you could have used Newton's laws to try and figure out the crate. So here's the exact same thing from assignment number 2, right? The crate leaves a ramp, right? It has an initial velocity of 0, and then it's going to have some kind of final velocity. With the ramp is going to have an angle, and it's going to have a rise or a height, right? Can we use energy of a system and the idea of conservation of energy to figure out its final velocity, right? Which is exactly what you would have done with Newton's laws, right? So yes, so at the top, you can see that the initial energy at the top, right? Internal energy is equal to the kinetic energy plus the initial gravitational potential energy, right? Which is equal to 0 plus mg initial y, right? So high, that's the height, mg height, right? On the other side, right? And then at the bottom, the energy final, right, is equal to the kinetic energy final plus the gravitational potential energy final, which, if you put it on the other side, if you sub in 1/2 mv squared final plus mgy final, mgy initial, which is the potential energy initial, right? And so what you can do is you can create the change in energy, the mechanical energy that's being used here is the energy final minus energy initial, which is equal to a negative force of kinetic friction times the distance being traveled, and then you solve for velocity final. All right, so pretty simple way of doing it. We've kind of talked about that before, where I said, okay, I have like a lot of potential energy at the beginning, and I kind of did a little example of that in one of our videos, where I kind of have, here's the potential energy because of gravity, gravitational potential energy, and it's going to transfer from gravitational potential energy into kinetic potential energy. And we can figure out the total transfer of energy, and then we're going to subtract the kinetic friction, the energy, because the work that's being done over the whole distance, right? Because that's what's going to be lost of kinetic the work that's being done from the friction force over that time. Okay, so and then one thing we could do is we could compare the result if the ramp was frictionless, what we do, and if the ramp has friction, we can compare one system to the other system. And then what happens to that energy? The energy is not lost; it's being transferred in terms of some kind of mechanical energy. So, for example, in terms of sound energy is being transferred out of the system because maybe it's going to screech on the way down the crate, all the way down the ramp, right? As well as heat, internal energy. Okay. Spring block collision. So here's something that we want to look at as well. And I'm going to zoom in here to see this. So we have a block with an initial velocity. All right. It's going to hit a spring in equilibrium. Okay. So at the beginning, the distance that the spring would have traveled is 0. It's not going to compress. It's in equilibrium. The block is going to compress the spring to some degree, right? It's going to go to its maximum compression, and then it's going to spring back. It's going to go beyond this and then spring into equilibrium again, right? When it does, it's going to transfer the energy back the other way to the block. So first, the block transfers the energy to the spring, and then the spring, if we were to consider this a perfectly elastic collision, which we're going to talk about next week, it's going to transfer the energy back out from the spring into the block and back in the opposite direction. Again, conceptual stuff. And it talks about how to do the concepts here. All right, what about power? Remember, power was the rate of energy transfer. So we can also define instantaneous power as the derivative of the total energy over the derivative of time, or the change of energy over the change of time. That's the total power of a system. We could say then that the average power is the total work done over the change in time. So work over time. That's the average amount of power that's being used. So instantaneous power is that, tangent to the curve, the energy curve that we're talking about. Again, we haven't done calculus, so this is really, talking at a very high level. How do I figure out the instantaneous power at a certain point in time? We can actually calculate the instantaneous power by using the limits. As the time approaches zero, limit as the time the change in time approaches zero of the total work over the change in time, and then we can figure out what the instantaneous power is, like this. Okay, where we have the total force vector, where we have times the total the velocity vector, and then we can find the instantaneous power. We talked about units of power before, which is a watt, which is a joule per second, how many joules per second we can transfer. So power is really transferring energy, right? That's what we're doing here. All right, so that is all the stuff related to conservation of energy, the idea behind it. If I could have fit it into the stuff from our previous lecture, I would have, but I thought that would have been an additional 35 slides of stuff that may or may not have been useful to you. And that's why I've moved it to this lecture, right? So we need to know about conservation of energy in order for us to do collision detection and response. And so this next part, where it says transition to next lesson, are some of the things that we need to know in order for us to, or reminded of, because we talked about mass before, right? And we want to understand these things, this idea, as we move into collision detection and response. So again, when we think about mass and inertia, they kind of mean the same thing, right? I want to talk about this a little bit with you guys. Remember that this idea of weight, right, in physics, this word is used to describe how the mass is, what it feels like inside of a gravitational system, right? That's what the weight is. So our weight is mass times gravity, mg, right? If you think about that. And so if we have a different gravitational pull, example, if we took our mass and you put it on the moon, then our apparent weight would be different. We talked about that. Similarly, if you think about this, when we think about inertia or mass, it's how hard it is to move our mass. How hard is it? The more inertia I have, right, as an example, is it creates a system of how hard is it? How much energy is it going to take for me to move my mass? That's inertia, right? Mass, we know, is a scalar quantity measured in units such as grams, kilograms, or pounds, right? And we know that weight and mass are proportional based on the gravitational energy that's in a system. Okay, so just kind of terminology here that we're going to be talking about. So how do we calculate momentum? So we talked about inertia. Inertia and mass are almost like synonyms. We can say, if I say inertia in your head, you should think about mass. It's mass, right? What about momentum? Momentum is really a product of a particle's mass and its velocity. The higher the velocity and the higher the mass increases the total momentum, right? So when we think about the second problem that I've given you on your assignment 3, think about increasing the velocity and think about increasing the mass. If I increase the mass and the velocity, I will have more momentum. When we think about momentum, the words in your mind should be, how hard is it to stop my mass with this momentum? How hard is it to stop? So, example would be, it is much more difficult to stop a 10-ton truck traveling at 1 mile per hour than it is to stop a toy car traveling at 15 miles per hour, right? Because a toy car has very little mass. It doesn't matter how fast it's going, right? Well, it does, but it's not going to be the same amount. Whereas a truck is going to be much more massive, And if I'm traveling at 10 miles an hour, as an example, or 1 mile per hour, it's going to be way more difficult to stop that because of the mass velocity. When you multiply mass and velocity together, you're going to get a much bigger momentum. And a good example of that is, how much does a truck weigh? If you think about this in your head, right? Let's suppose a truck weighs 10 tons, okay? I'm just putting it out there, 10,000 kilograms, all right? We'll say 10 metric tons. If it's weighing 10 metric tons, right, 10,000 kilograms, right, and if I'm going at 1 kilometer per hour, right, and if that's the momentum, so I have, my momentum is going to be measured as a unit of, let's say, 10,000. I have 10,000 in terms of momentum units, call them whatever you like, or kilograms per kilometer, right, as an example. Or if you think about this, it's basically how much kilograms per kilometer per hour is what we're talking about, right? That's momentum. So think about that, right? Whereas a toy car might only have, maybe not even, let's say it's a heavy toy car, so it's a kilogram, all right? Kilogram. And it's moving at the same rate, 1 kilometer per hour. 1 kilogram, 1 kilometer per hour, it's got one unit. 10,000 units, 1 unit. So we can easily say that the truck has way more momentum. It's way harder to stop a truck than it is to stop a toy car. Even if you increase the speed of the car to 10 kilometers an hour, it's still 10,000 units to 10 units. It doesn't equate. The truck is way harder to stop than a car, the little toy car, right? And in your mind, this is how you should think when it comes to the second problem that I've given you. Again, this is why in feats of strength, people are able to pull a truck with their teeth. How does this work? Once they start the truck going, they've imparted energy to the truck, right? Which is crazy, because the truck just needs to start rolling. Then it's easier. Once the truck has started to roll, then you can keep a truck rolling. It's just that initial pull that's important, okay? But then it's going to go on its own momentum afterwards, which is what the idea is here. Okay, the most important thing to think about momentum is that it's conserved. Okay, so the amount of momentum is conserved. We're talking about conservation of energy here. So when we calculate the momentum, that means that in the absence of some kind of external force or influence on a particle, or for that matter, the entire system of particles, the total momentum is unchanged. Total momentum is unchanged. So again, when you're dealing with things like cannonballs, it's not that very useful to know, because cannonballs, they have outside influence, the force of gravity, right? But when it comes to other things, this idea of momentum makes sense, okay? And again, we're going to think about it for ourselves in a video game. Most of the times, we're not going to think about air resistance or things like that, because it's going to be baked into our velocity equations. Okay, we're not going to try and make it too complex. Our game system is going to be realistic, simulating a simulation, but it's not going to be oppressive in terms of the way we code. All right. So once we start looking at collisions, though, that's when we start thinking about momentum, because now we're talking about energy transfer, and what happens to that energy? Some of it's going to be lost. Why? It's going to be lost as we transfer energy from the object into the wall. And some of this is this, right? It goes back to Newtonian physics again. For every action, there's an equal and opposite reaction, right? Think about that. Equal and opposite reaction minus the energy loss, which is where we want to add things in for the idea of energy transfer or energy of a system. Okay, so how do we use our conservation of energy to solve ballistics problems, which is what we want to talk about today, this idea of particle motion, if you will. So again, think about what I'm trying to do. If I have a projectile flying freely, then the energy must remain constant. So if there's nothing acting on it, so there's no gravity, a projectile's flying in space, right? Then there's no energy transfer. It's just going to keep on flying in the same direction. A body at rest tends to stay at rest. A body in motion tends to stay in motion unless some other energy or something applies, a force is applied to the body. It's going to keep going in the same direction. Okay? So again, think about, I have a cannonball. When I shoot a cannonball up into the air, kinetic energy is transformed to gravitational potential energy, or UG. And when it flies back down, potential gravitational energy is transferred back into kinetic energy. And it's going to keep on doing this. Minus some kind of energy loss if it's hitting the ground and bouncing. If I've got bounce, I've got clack, I got sound. If I've got bounce, unless it's perfectly elastic energy, not elastic collision, for example, some kind of India rubber ball, right, that's going to maintain a lot more of the energy, because both the surface of the ground, let's say, is bouncy, and the rubber ball is also bouncy, like extra bounce, as an example, then what's going to happen is, you're eventually going to still slow down. There's still going to be energy loss. It's not going to last forever, but the bounce is going to last a lot longer. The energy loss is going to happen over a longer period of time. Okay. So, for example, you can ask how high a cannonball will climb if I fire it straight up. If I fire the cannonball at 20 meters per second, suppose also the cannonball has a mass of m, whatever m is. Okay. The ball's initial kinetic energy is 1/2 of mv squared and is therefore 200 m. Does that make sense? Because, remember, 1/2 mv squared, we put in the velocity, the initial velocity is 20 meters per second, we're firing it straight up. 20 times 20 is 400, 1/2 of 400 is 200 m, 200 times the mass, right? Again, you're going to measure the potential energy from the muzzle of the cannon, right? The muzzle velocity, if you will, right? So at the point at which the ball leaves the cannon, the gravitational potential energy is 0. And therefore, its total energy is the sum of the kinetic energy and the gravitational potential energy at all times during the flight. It all has to be 200 m. It's the same amount of energy when you add those two pieces together. It's just like how much of that energy of a system is inside of potential energy and some of how much is in on the kinetic energy side, right? As it flies up, potential energy increases and kinetic energy decreases because it's fighting gravity. And so we can say that at the top, right? At the top, we know that the gravitational potential energy at the top is going to be maximum, right? And the kinetic energy is going to be minimum, right? So we can say that if we use mgh is equal to 200 m, we can think then that h, if we cancel out the m on both sides, right? Because mgh is gravitational potential energy, right? We can take the m from this side and the m from this side, they cancel out, and then we have gh is equal to 200, right? So then if I take the total height, I want to find the total height it'll go when I fire a cannonball. I take 200 and divide it by gravity, which is approximately equal to 20 meters. If we say that gravity is 10 meters per second. All right, so that's what the approximate height would be at the top of the where the gravitational potential energy would be the most, and where kinetic energy would be 0. All right, and again, like I said, notice that the mass term cancels out on the two sides of the equation. And this is what makes it easy for us to calculate things by using this conservation of energy idea, right? Since the trajectory of the projectile is independent of its mass, this is to be expected because we don't care about mass. Mass is it's a factor when it comes to momentum, but mass is not a factor when it comes to energy. In other words, like kinetic and potential energy. It doesn't matter. Okay, what about if a cannon's fired at an angle? How do we figure this out, right? So again, suppose that the cannon now is fired at 30 degrees to the horizontal. So now it's a constant horizontal velocity of 20 meters per second again, right? Times cos of 30 degrees, because it's v cos theta. That's the equation. Then what we're going to get is 17.3 meters per second across the horizontal on the x-axis is what we're talking about here. All right, let's keep that in mind. So the kinetic energy is 1/2 mv squared. We know v is 17.3 meters per second on the x-axis. which means that the total number of joules is 150 m joules, where m is mass, whatever the m is. We don't know what it is. And therefore, since the total energy must still be 200 m, right? It must still be 200 m because it's going to climb to a total height of whatever that's going to be, right? From the previous equations. We can say that 150 m plus mgh is equal to 200 m, right? And therefore, we know that if we balance both sides of the equation, that gh is equal to 50, and so the height is approximately equal to 5 meters. So pretty simple, and we just use energy of a system. We've not used the kinematic equations at all. One thing to note is that energy tells us nothing about time. It doesn't tell us anything about time at all. It just tells us about 1/2 mv squared, right? We know kinetic energy is there, but it doesn't tell us anything about time at all. But we can use it in combination with other formulas to give us time. All right, that's really all I wanted to talk about today, guys, as well as the assignment. Are there any questions about conservation of energy? The idea that energy is neither created nor destroyed. This is really what I wanted to talk about today. Okay, I'm going to stop recording now, and then I'll take questions, right, that are local to the people that are in the class. Otherwise, that's it for this lecture. I'll see you guys during the next lecture. Please connect with me if you have questions around your assignment 3 or any other questions related to assignments. I'm going to stop recording now.